Okay, so we are going now to the last part of the first lecture, and this part will be about two empirical examples. So what we are going to cover here is like two examples concerning the forecasting of large dimensional realized covariance matrix. Okay, so before we start to look into the applications, let me give you a brief overview about what a realized covariance matrix is. Okay, so imagine that we have, like in a day, say like t equal to 1, day 1, we observe over the day, every minute, we observe returns of an equity. So this is the return of minute 1 on day t, this is return on minute 2 on day t, minute 3 on day t, so on and so forth. So we meant the last one will be return of minute 390 of day t. Okay, so this, like New York Stock Exchange, will be open from 9:30 until 4 o'clock. So we have like 390 intraday returns. Okay, it has been shown in the literature, if I want to compute, to have an estimate of the volatility of returns on this specific day, what I can get, I can take these intraday returns here and compute the sum. So I equals to 1 to 390, and I'm going to sum the square of these returns. This is what we call the realized volatility of day t, or realized variance to be more precise. So this is the realized variance. The realized volatility we call, that's the square root of RVT. Okay? So this is under certain assumptions. This is an unbiased estimator of the daily variance, exposed variance, and also consistent to the integrated variance. Okay, but we are not going to go into such details. I just want to show what this estimator is. So now suppose that instead of having one day, okay, we have like multiple days up to day capital T. So we have a time series of realized volatilities, okay, that computed from these returns. And we can also say that at day t, we have like RT is the vector, okay, of these returns. R1t, R390t, okay? So we can have this for stock 1, so we can label this stock 1, and we can have another vector for stock 2, for instance, okay? So this will be the returns for stock 1, and you can have the same thing for stock 2. So we can compute the realized covariance of day t as the sum of phi equals to 1 to 390, okay, of these returns 1, okay, 2 transpose. Okay, so this will be a 2 by 2 matrix. We have the covariance of these two returns. We have the variance, so this will be a 2 by 2 matrices. We have in the diagonal we have the realized variance, and in the off diagonal we have the covariances. Okay, so in this case this is 2 by 2. We can define the realized covariance for multiple assets. So if we have any different assets, we are going to have a realized covariance matrix that will be n by n at time t. So imagine now that we observe this over time, so we can have like at day 1 we have a matrix, at day 2 we have another matrix, at day 3 we have another matrix, day 4 we have another matrix, so on and so forth. So this we can label this sigma of day 1, here will be sigma of day 2, sigma of day 3, sigma of day 4, sigma of day capital T. So this is a sequence of time series of matrices. Okay? So what we want to do in this application? We want that based on a history of realized covariances, we want to forecast the future. We want to know at day t plus 1 what's going to be sigma t. So we want an estimator or a forecast for the sigma 1 day ahead, or we can do that for 1 week ahead or 1 month ahead. So we want to forecast this. And why machine learning is important? Because we have these matrices can be very large. Okay? These are n by n. So if you have like 30 assets, you have 100 assets, you can see how many different entries you're going to have in these matrices. So this is a huge problem in terms of estimation. Okay? So that's what we are going to do in these applications. Okay? So there are two applications. One is for a more limited set of assets. We are going to consider just 30 assets that belongs to the Dow Jones Industrial Average. In the second application that I'm not going to explain in this video, but you can follow just looking at the slides, and I'll be happy to tell you about them during office hours or any other meeting that you want to have to discuss about this other application. And in the second application, we consider almost 500 assets, so it's a much bigger problem, okay? But let's concentrate now in the first one, just with 30 assets, because this will be already a complicated problem, right? Okay, so the application, the first application is based on this paper I published with two co-authors, Laurent Callot and Anna Skok, and it's published in the Journal of Applied Econometrics a couple of years ago. Okay? So the idea is that we have these realized covariance matrices, okay? And we have this time series of realized covariance matrices. And one stylized fact in the literature is that in order to model the time dependence of the entries of these matrices, you need a model with a lot of legs. Usually you need more than 20 legs. Okay? How we are going to do that? So let's call sigma t the realized covariance matrices at day t. Okay? And so here is our realized covariance matrix. And then we are going to take and we are going to vectorize sigma t, but just keeping the unique elements. So sigma t is a symmetric matrix, so we just want to get the unique elements, and we are going to call this yt. And then we are going to model yt as a VAR of order p. It's a vector autoregressive process where yt depends on past yt. And how many legs we are going to use, this is determined by p, and as I mentioned here, usually this p can be very large. Okay? And this is a vector of constants that we do not know, we have to estimate. These are the intercepts, and these are matrices, so we have like p matrices phi. Okay? Each one of these matrices is this is a square matrix of parameters that has like dimensions q by q, where q is n times n plus 1 divided by 2. Okay? So we have in this system, this is a system of equations, we have n times n plus 1 divided by 2 equations, and the total number of parameters is this big number here. Okay? Why is that? Because we have squares here, see? So this is be like n plus 1 divided by 2, everything squared, because this is a square matrix. So we have like p of those matrices, because we have like p legs, plus we have the entries of the intercept. So it's a huge system. A lot of parameters to estimate. So imagine that you have n equals to 30, that's what we have in this paper, so you can do the computation and you're going to see that the number of parameters to be estimated is just enormous. So we cannot just come here and run OLS. There's way too many parameters to be estimated. So what we are going to do, we are going to use the techniques that I showed you in the previous videos. So this penalized regression approach, basically we are going to look at lasso and adaptive lasso. We look this into very detail in the paper. There are many results in the paper. Here I'm going just to highlight how these models can be useful, right? So another point that's important to notice here is that in this vector y here we have two sorts of elements. We have the diagonal of sigma, these are the variances, the realized variances, and we have the off-diagonal elements, which are the covariances, okay? And it will be interesting to see the interaction between these two groups of elements, how covariances affect variances and vice versa, okay? So this will be important in our analysis here in the results that I'm going to show you. So we have 30 stocks. The sample starts in 2006 and goes up to 2012. We have 1,474 daily observations, okay? The daily realized covariances are estimated with a little twist, not exactly the estimator that I described to you, because there are some issues in intraday data, but there's no point in getting into detail about that. Just focus on the overall model setup, okay? So what we are going to do, we are going to construct a rolling window. We are going to take 1,000 observations, okay? We are going to estimate that huge VAR model by lasso or adaptive lasso, okay? And we are going to make forecasts for 1 day, 1 week, and 1 month ahead, okay? For the full matrices, okay? And then we're going to keep this forecast. This window will move 1 day. We are going to re-estimate everything again and compute the forecast. And we are going to do that until we reach the end of the sample. So we have many forecasts and we have many estimated models. One model for each estimation window that we have, okay? And we split the stocks into different categories, because this will be useful to understand what's going on, okay? So we have like 8 categories. These are the 8 categories here. You can see in this table here. So we have like 2 equities belonging to basic materials, 2 firms belonging to technology, 3 belonging to consumer cyclicals, so on and so forth, okay? First results. So the first results are the following. If we look at the estimated models, okay, over these rolling windows, okay, we run lasso, and as I mentioned to you, what lasso will do? Lasso will estimate a large number of parameters as 0 and will keep a small amount of parameters different from 0. So it will be interesting to look at which parameters are in the end estimated differently from 0, okay? So how we are going to do that? We are going to look at every window, every estimation window. We are going to look which are the parameters that are estimated as 0 and which are not. And we are going to look, is this a parameter related to a link between a variance to a variance, a covariance to a variance, a covariance to a covariance, or a variance to a covariance. Okay? And also how different sectors are linked to each other. So what this matrix here, the matrix that you are looking on the slides is the following. Each entry of the matrix is the frequency, okay, a coefficient that links in the first panel, that links a lagged variance to a current variance. So it's variance affecting variance, but we split that effect into different sectors. So it's like here is the basic material past variance affecting current basic materials variance. Here is basic materials variance affecting consumer non-cyclical variance, so on and so forth. So the diagonal is the same sector effect. As you can see, you have high frequencies here. See, in most of the cases, apart from consumer non-cyclical, past variance, its own variance affects future variance. That's the persistence that we observe, that's expected, right? We do not have really big numbers outside the diagonal, apart from several cases, but they're not too small. So it goes from 20% to 50%. In some cases they are very small, like here, but can be large, like here, like consumer cyclical past variance affecting consumer non-cyclical variance. Okay? But overall, what we can see here, that's past variance is important to predict future variance. So variance affects variance. But let's now move to lagged covariances. Here, how lagged covariance, the off-diagonal element, affects a diagonal element. Okay? So you can see here, mostly zero. So off-diagonal elements are not important for diagonal elements. So past covariances have no effect on the future behavior, the future dynamics of variance. This is an interesting result. Okay? Now, let's look the other way around. Let's take as a dependent variable the covariances. And let's see how past variances and past covariances affect current and future covariances, the off-diagonal elements. And surprise, surprise, what we see is that variance affects covariance. See? Especially if they are in the same sector. There are some surprising things here, like basic materials affecting energy in terms of covariances. Okay? And even more surprisingly is that, of course, this is not a matrix of zeros, but the numbers are pretty small. So past covariances are not even much important to forecast covariances. So off-diagonal elements, the past off-diagonal elements seem pretty much irrelevant. This is a finding average over all the 1,000 rolling windows that we have. So it's kind of a pretty robust result, okay? And this is interesting. So all the predictive powers, the power seems to be in the past variances and not in the past covariances. And this holds both for future covariances and future variances. Okay? Remember that because in one of your future assignments, you are going to work with covariances. So this is a nice way to simplify your models, okay? To base your models on that specific result. Now, how big are these equations, the estimated equations? So here I'm plotting like 4 graphs. So these first 2 graphs here, the first column, are for diagonal elements, for the diagonal equations, and here is for the off-diagonal equations. So what I'm showing is the average number of non-zero parameters at every estimation window over the sample. And this is average over what? Over all the equations, over all the diagonal elements, over all the off-diagonal elements. So you see here that although we have a problem with thousands of parameters, the size of the equations are pretty small. If you have a VAR1 as a model, or if you have a bigger model, a VAR20, that's a huge model, still you have like around 20 parameters. So it's pretty parsimonious model that you have in the end of the day, and this does not change much, right? So here we are oscillating between 11.5 and 12.5, here from 20 to 24 is not a huge difference. There's some kind of stability, right? When we look at the covariances, the number of parameters are higher, the number is higher, but still parsimonious if you compare to the total number of admissible parameters, right? But what you see is that there's a kind of clear 3 regimes. Something in the early 2010, then like the 2/3 of the sample, almost like, not 2/3, a little bit less than that, but like more than half of the sample, you have like one regime here, and then in the end, you have another regime here, and it's a kind of a clear drop. Here you see something that's much more, it's very smooth, and here you have a huge drop in terms of equation size. So the model, that's an interesting thing, because there's some instability in terms of which model Lasso is selecting, okay? But there are some, from one day to the other, from one window to the other, you can have a huge change. Something happened that the structure of the model completely changed, okay? This is the fraction of parameters that change between being 0 to non-zero, because one of the criticisms is maybe Lasso is too unstable, so every time the method is estimating like crazy different parameters. And what you can see here, that's a lot of stability, right? So you don't see a lot of parameters changing from 0 to non-zero, okay? So there's kind of an instability of which parameters are relevant and which are not. So which are the relevant predictors in this model, okay? And this is the likelihood, just to look how the likelihood evolves. And this is the selection of the penalty parameter. You see, there's pretty stable over the sample. In the end of the sample, you have an increase in the lambda, so it increased the penalty, which it makes sense with that result, because you see that here in the end, from that point onwards, there's a huge drop in terms of the number of parameters. Why is that? Because lambda is growing. We are including more penalty in the model, the estimated lambda. We are going to learn during the course how to select that lambda. It's a data-driven procedure. We let the data speak, okay, about which is the best lambda. And it changes a bit in the end of the sample as it shows there in the slide, okay? All right, so, but which variables are being selected? So here what we are showing, in this axis here, we have like the time of the estimation window, when we are starting the forecast, okay? Here we have how frequent, okay, the elements of each one of these stocks is being selected overall. Okay, so the darker is the blue in that figure. It means that these stocks are being selected for most of the equations, for all the other stocks. And there's something that clear blows from this picture, and is IBM. Look the pattern of IBM. It's kind of stable all over the estimation windows, okay? And it's much darker, the blue, than any other. It's followed by Alcoa, okay, AA, but it's much, so it's been selected in most of the cases. So it's working like kind of a common factor, right? And that's kind of strange. Why IBM, and followed by AA, they have this power? Because you see all the other equities, the blue here in the picture is much lighter. Okay? So the selection frequency is much smaller. And then we take a look at special cases here. So this is Alcoa, and how often these covariates are being selected. So you see here IBM is being selected a lot, and we have this block here being selected a lot, and this block here being selected a lot. Okay, so you see, but there's a lot of sparsity. And we have that for IBM, we have that for JP Morgan, and we have for Coca-Cola. Okay? And Coca-Cola is interesting because look at here. Here's Coca-Cola. So nothing, something in the end. But IBM is always there. Okay? So this is kind of weird, but that's what the selection mechanism is doing. So past Coca-Cola is not helping to predict Coca-Cola, but the volatilities and the covariances and the variances of other assets, they are helping to predict. That's what Lasso is selecting. But what you can see, that it's a very sparse structure. Okay? So one thing that we imagine doing that paper is, okay, maybe what's going on is that IBM is very related to the S&P 500 index, or the market index. So what IBM and Alcoa, what they are doing is like capturing the effect of an index. Okay, so basically we also plug into the model the variances and the covariance of the S&P 500 with all the other stocks. And you see now we are measuring here how often S&P is being selected in variance equations for all these each one of these variables. And you see it's not being selected everywhere. And most importantly, it's not being selected for IBM. And if we do the opposite exercise, we look at how often these covariates are being selected to model the variance of the S&P 500. Almost nothing, very sparse. We have something here, but IBM is not there either. So this is a kind of a weird fact. Okay? Why we have this pattern, we couldn't find a reasonable explanation, but the fact is that these variables are helping to forecast future covariances and variances, and that's the point. Okay? We have in the paper a bunch of forecasting results, like point forecasting results with different models. Okay, if you just look like mean squared error, median squared error, what we are going to see, like all these numbers that you see in this table on the slide, is that it's really difficult to distinguish between models. If you do Lasso, adaptive Lasso, or if you take a more naive approach, the performance is somehow similar. But the gains will come from a portfolio optimization. So if we look at a mean variance approach, where we are going to select the weights of a portfolio, like minimizing the variance of that portfolio, okay, so we have lower, but subject to a return target and restrictions on the weights. The weights should sum up. One, we have a leverage restrictions, so we cannot have more than 30% of leverage. And also, we want diversified portfolio, so we do not want to allocate more than 20% in one asset, okay? So what we are going to do, we have to plug in here different forecasts for the covariance matrix. So we are going to compare lasso family, different forms of lasso, with other benchmarks. What are the benchmarks? Traditional volatility models that you find in the literature, okay? Also, we don't have time to get really into details. Anyone that is interested can drop me a message and then I can explain all the details of these of the paper, right? But the thing that we should look particular is this last block here. This is the economic value. How much an agent will be willing to pay, an investor will be willing to pay to have our VAR lasso based model as compared to benchmarks. We have like 3 benchmarks that volatility does not change from the previous volatility, and 2 latent volatility models, DCC and exponential smoothing, okay? Which is not, these 2 approaches here do not explore intraday data. So what you can see is that all these positive numbers means that the investor will be willing to pay something to have our model. So we have significant gains, economic gains, and this can goes up to something like from 10 to 15, 11 to 16. The differences between these 3 panels is that the risk aversion. How much of risk aversion the investor will have. Okay? So, but the message here, the takeaway from this table is that we are improving the forecast. And if you look here also, we have large average returns, we have large accumulated returns as compared to other approaches. We can have up to 30% of accumulated returns, when the no change will have like 7, and the traditional methods will give you negative returns, okay? And we will have that with restrictions on leverage and also with a very low turnover. Of course, we are including transaction costs here, okay? So basically, this is an illustration that we have a difficult problem with lots of variables, okay? And Lasso can help us here, and we can compute reliable forecasts for this large data set. Okay? So that's the message. Okay? There's a second application, very similar, but here what we are going to do, that we are going to go much larger. Instead of considering 30 assets, we move to almost 500. Okay? I'm not going to discuss this in this video, but I will invite you to take a look at the slides or take a look at the paper. The paper, everything is explained, and I'll be very happy to discuss this paper with you. If you wish, we can have a Zoom meeting and I can explain all the details of the paper. So thank you very much for that first lecture. In the end of these slides, you are going to see all the references from this first lecture, okay? These references are all in our Google Drive, where you can download all the references for this first class, okay? And I've also put some questions for you in the very last slide for you to think about, okay? So see you on Friday in our meeting, where we will discuss what we saw today in these 4 videos in this first lecture. So thank you very much and see you on Friday.